My name is Stephen, and in this short module we'll learn how to use electrochemical polishing in sulfuric acid to clean our working electrode. In addition to mechanical polishing, which we covered in a separate video, we can also clean the surface of our working electrode using electrochemical polishing. This is particularly useful in situations where mechanical polishing may destroy our electrode surface. Furthermore, we can use electrochemical polishing to find out some more information about our electrode, such as the material and the surface area. Electrochemical polishing is usually achieved by performing continuous cyclic voltammetry in a solution of sulfuric acid. In this video, we will be using 1 molar sulfuric acid, which we will now add to the cell.
We don't want to study the influence of oxygen reduction, so we are going to remove all of the oxygen in our solution by purging it with argon. This gas is denser than air, so as well as displacing the oxygen, it forms a blanket on top of the solution that hinders reoxygenation. We are also passing the argon through a specialized glassware item called a Drechsel bottle, which humidifies the argon and prevents excessive evaporation during purging.
Our working electrode will be a platinum macro electrode, which we previously mechanically polished. We will also be using a silver-silver chloride reference electrode and a platinum counter electrode.
We can add all of these electrodes to the cell containing the sulfuric acid. We will start our cyclic voltammetry at open circuit potential and continuously cycle between positive 1.3 and negative 0.2 volts versus silver-silver chloride until we get a reproducible voltammogram. At the beginning of this procedure, the features of the voltammetry are poorly resolved. After some time, the features appear more defined and the peaks we observe become stable. So what does the shape of the voltammogram we get on the final scan mean? Starting from open circuit potential and going positive, we see a broad peak corresponding to the formation of platinum oxides on the electrode surface. On the return scan, these oxides are reduced and the platinum surface is replenished. Adsorbates on the surface may have a different affinity towards platinum oxide than they do for bare platinum, and vice versa, so the continuous formation and removal of oxides allows for the desorption of adsorbates and cleans the surface of the platinum. This allows for the formation of a platinum hydride monolayer, which we see in 2 distinct peaks, one corresponding to a weak adsorption and the second corresponding to a strong adsorption. These peaks are mirrored during removal of the platinum hydride monolayer on the reverse scan. Since these peaks correspond to the formation of a monolayer, their accurate measurement can be used to estimate surface area. We need to be careful about the selection of our potentials, since if we go too positive we can induce involution of oxygen and later get currents related to oxygen reduction, or if we go too negative we can induce hydrogen evolution and later get currents related to hydrogen oxidation. The response we have studied so far is indicative of a polycrystalline platinum surface. Single crystal platinum surfaces produce sharp peaks in specific potentials that differ from other orientations. The use of other materials results in a characteristic voltammogram for those materials based on surface electrochemistry. For example, on gold we see oxide formation and removal, but no hydride monolayer peaks, and on carbon, neither oxygen nor hydrogen evolution are visible, but we can see some small peaks corresponding to quinone electrochemistry.
Thanks for watching this video on electrochemical polishing. If you haven't already, why not watch our video on mechanical polishing that's also on this course, and I'll see you next time.